Applications of Gauss law. In the previous lecture, we discussed what is Gauss law, different form of Gauss law, and the significance of law. Today, we will discuss some important applications of the Gauss law. Through this lecture, we will able to learn applications of Gauss law for calculation of electric field under various charge distributions. We will learn how to imagine the Gaussian surface and the way to calculate the field. We have learned what is Gauss law for electrostatic in the last lecture. Yes, in Gauss law relates the flux of any electric field through an closed surface and the net charge enclosed within the surface. The Gauss law is used to calculate electric field whenever some charges are present at some place, then we assume a closed surface around them, and then we use Gauss law, which relates the flux of the charges inside this with the surface. So the Gauss law is phi is equal to q over epsilon 0. Here phi is flux. Flux is give the idea of number of lines. I suggest you go through the previous lecture before learning this. Now this q is basically representing sum of all charges present. You can use sum also. This law states that the total flux of electric field E over any closed surface is equal to 1 upon epsilon 0 times the net charge enclosed by the surface. The closed imaginary surface that we have assumed and termed as Gaussian surface, this should be closed. The Gauss law tells us that the flux of E through a closed surface depends only on value of net charge inside the surface, and this doesn't depend on location of the charge. Charges outside the surface will not contribute. Only those charges can contribute which are inside this. We have learned basic details in the previous lecture. This is just to memorize. Now this law can be used to calculate electric field and various conditions. We will discuss in coming slides. We are discussing here application of Gauss law. Gauss law can be used to solve complex electrostatic problems involving unique symmetries like cylinder, spherical or planar symmetry. Also, there are some cases in which calculation of electric field is quite complex and involves tough integration. Gauss can be used to simplify evaluation of electric field in simple way. We can apply Gauss law in the following way. First, choose a Gaussian surface such as evaluation of electric field become easy. That is very tricky. What surface should be chosen? It should be symmetric or it should be closed and it should simplify the problem. Then make use of symmetry to make problem easier. Remember, it is not necessary that the Gaussian surface to coincide with real surface. That is, it can be inside or outside the Gaussian surface. So it is interesting here. First thing is check the surface and then do the things. In this particular case, we are studying many applications like the charges are arranged in the form of wire, then charge is spread on the sheet, and you are having two sheets or several applications. First application we are discussing here, electric field due to infinite long straight charged wire. It is a common application of Gauss law. Suppose you are having a long wire and you want to calculate the electric field due to this long wire. Here we have considered a long uniformly charged wire having a constant linear charge density lambda. Here the density is charge per unit length. We have taken charge as lambda charge per unit length. And let you are having this wire and you want to calculate the field of this wire at this place P. P is distance R from here and the wire is very long on both the sides. If you are taking this case and the point is about the distance of R, then you can consider a cylinder about this. Here we have assumed a cylinder of length L and radius R, closed at each end by plane caps normal to the axis chosen at Gaussian surface. And consider a very small area ds on the surface at this place where we want to calculate field at P. By symmetry, the magnitude of electric field will be same at all points on the curved surface. I think all of you are aware with this. This is your wire which is shown here with by the positive, 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 and due to this electric field may be here and may be here. The magnitude of electric field is symmetric at all points on this curved surface. Curved surface is similar. The direction of electric field is radially outward if the charge is positive. If we take the negative charge, then the direction will be radially inward. I have taken positive charge, so it should be outward direction, radially outward direction. The field is there. We have chosen a small surface element ds, where we want to calculate at P, about P, where we want to calculate electric field, and the ds is in outward direction. In our case, outward direction means this direction. Similarly, E also is in this direction, as we have told you that whenever we are having wire, long wire, it should be in radially outward direction. So both are in same direction. Now we can say then on the curved side, E and V along in the same direction. The electric flux phi through curved surface can be written as is EDS cos theta. We have done this in the last class. Then when area element is given, electric field is given, and the angle between them is theta, then electric flux can be calculated EDA cos theta or E dot dA. In our case, both are parallel. Since both are parallel, the theta will be 0 and your values reduce to EDS. Now, since this cylinder is a symmetric Gaussian surface, which is a viable choice, then in place of ds, if we integrate the ds, then E can be taken out because E is same at all places. So d gas can be done as 2 pi r L. The surface area of the curved part is 2 pi r L. E and ds are right angle to each other on plane caps. Yes, there are two plane caps here. One is here and second is here. In both cases, the perpendicular, the direction of the area element is in, and electric field with this. So both are perpendicular to each other. Since both are perpendicular to each other, the angle will be 90 and cos 90 will be 0. So total flux calculated by only the curved surface. There is no contribution from both top and bottom plane surfaces. So the total contribution, net charge enclosed, can be calculated as we have shown that the charge density is lambda per unit length, and if we know the total length, that is L, then this can be done. The Gaussian surface, charge on Gaussian surface can be done as this lambda. So now we have Q is equal to lambda L, and we also have phi values. So put this value here. E into 2 pi r L is equal to lambda L over epsilon 0. And from here, we can find out the value of E. E is equal to lambda over 2 pi epsilon 0 r. This is the value for infinite charges in a linear line. along the curved surface. The direction of electric field is radially outward and its line charge is positive and inward. If the line charge is negative, then the direction of electric field will be inward. So one thing is sure, if you are having a charged particle in the form of wire, then you can calculate field at any point which is at a fixed distance from there, and you can also see just by checking the whether it is a positive or negative, whether it is outward or inward. Another thing that you want to check is electric field due to a infinite charge plane sheet. Suppose you are having a sheet like a sheet of plain paper and the charge is distributed on the plane sheet. Then how to calculate electric field using Gauss law? Yes, the electric field can be calculated. One thing is, if it is positive charge, then it will be outward. If it is negative, then it will be inward. First thing is. The second, you have, if you want to use Gauss law, then you have to think over the Gaussian surface, then use the Gauss law. In this case, we consider an infinite plane sheet of charge with surface charge density sigma. And let P be a point at a distance r from the sheet and E be the electric field at P. If E, we are considering on one side E, and on both sides at the same distance, the field will be same. And consider a Gaussian surface. Yes, we have to consider a Gaussian surface to calculate electric field. Here we are considering a Gaussian surface in the form of cylinder. So that is important. Very important thing is, whenever you have a problem, you have to think about Gaussian surface. Here we are talking Gaussian surface in the form of cylinder of cross-sectional area A and length 2r perpendicular to sheet of charge. In this case, we assume a cylindrical Gaussian surface of the length 2r, r on one side, second r from the suppose downward side and r on upward side, with the cross-sectional area A. By symmetry, we know that the electric field at right angle to the end caps and away from the plane. So we have shown here on both the side E is away from the plane and the outward side. Its magnitude is same at P and at P prime. Why I am saying this? Because both are at the distance r. P point and P prime point, this is your P prime. So this is at r distance from the sheet of paper. Similarly, this side is again r distance from the sheet of paper. So both are having same field and E is the outward. So if you want to calculate total flux, the flux is equal to E dot ds, integral of E dot ds at point P and integral of E dot ds at point P prime. Here we are assuming there is no angle between the area element and this electric field. That is why we are taking this as 0. There is no, because area is perpendicular for ds unit vector is perpendicular and which is same in the e direction. So both are true. So finally, we will have Ea cos theta and Ea. And here we will finally reach to this Ea. Ea and Ea may be equal to 2Ea. So the total flux is 2Ea. If sigma is the charge per unit area in the plane sheet, yes, as we want to use Gauss law, so we must have charge, what much charge is there. And in the previous case, we have assumed this lambda per unit length, since we are talking about length. But here we are talking about the sheet, then we have to take per unit area. If sigma is the charge per unit area, then net positive charge within the Gaussian surface can be written as sigma A. And using Gauss law, we can write this 2Ea, just we have calculated flux, that flux should be equal to sigma A over epsilon 0, because Gauss. If this is there, 2Eas we have taken in the first previous slide, we have calculated 2Ea, then by this you can calculate E. So if the charge is distributed on a sheet, then E is, it can be done as sigma over 2 epsilon 0, where sigma is charge per unit area. So you have seen here, it's a very simple method to calculate electric field. Gauss law provides us very simple way to calculate electric field. We have done two topics. One which is calculation of field due to when charge is in wire, it's adjusted along a wire, and second which is charge is on sheet. So in this lecture we have studied the calculation of electric field at two cases: when the charge is aligned in the form of wire, and second when the charge is spread on the sheet. And we have learned here how the Gaussian surface can be chosen and how the electric field can be assumed. We have learned here that electric field from positive side is always in outward direction, and from negative side is always in inward direction. So we have also seen here, and this is the method of using Gauss law is very simple and convenient as per the other methods. By using some symmetry rules without doing any complex mathematics, we have analyzed the things. We got the results in an easy way. In the next lecture, we will discuss few more complex problems, and then we will do some exercises on calculation of electric fields under various conditions. Thank you.